on, seriously, who calls it a transistor? Welcome to part 2 of the emitter feedback transistor. In this part we'll look at both temperature stabilization and the constant current effect of the transistor. Let's get straight into it then. Slide number 1, beta box revision. You'll recall that in part 1 we saw this same circuit, 2.2K in the emitter, 1K collector, 1 megohm in the base, and 2 different supplies. And we were able to avoid using Kirchhoff's equation on it, and we used the beta box instead. Remember, Kirchhoff's equation goes something like this. You'd have potential rises and potential falls. So you've got a potential rise of 15.3 volts. You'd have to subtract the potential fall of the voltage across the 1 megohm, the potential fall of the emitter diode, 0.7, you'd have to subtract, and you'd also have to subtract the voltage across the 2.2K resistor to end up with 0 at the end of the equation. And then you can transfer things from one side of the equation to the other, like the voltage, which we did, 15.3 minus 0.7 was 14.6, is equal to the voltage across him plus the voltage across him. If you can, avoid Kirchhoff's equations wherever you can and use the beta box. It was so much easier. In the beta box, all we did, we got that resistor there and we divided it by the beta. Then we got that new resistance and we added it to the resistance of the emitter circuit, and then we divided them into 14.6, and that gave us straight away our emitter current. So here's another slide from the previous part 1, and again showing that the emitter current is given by 14.6 divided by that equivalent resistance, REQ, of 5335 ohms to give 2.74 milliamps. I think the simulator gave us 2.6 milliamps. Very, very close indeed. Once we've got that, knowing that IE is equal to IC, we can put that current into the 1K resistor, get the voltage across the 1K resistor, subtract it from 15 volts, which I've done here, to get 12.26 volts on the collector. Very, very tidy, very nice, very easy to work with. In this PowerPoint, one of the key features is thermal stabilization. So I've got here a very stable circuit under thermal conditions. So as transistors and diodes are in circuits and they start working, they start to get warm. And as they get warm, the turn on of the diode or the transistor junction becomes smaller, and beta in a transistor starts to develop into a higher value. So while at room temperature we've got a DC beta here of 319, at a higher temperature the beta for this transistor that we use, the BC547, would be much higher indeed. In operation, the transistor becomes warm, as I said, and its beta increases. As such, more IE flows and VE increases, the voltage across the emitter resistor. VB has to follow that because what voltage we've got here is coupled via a diode junction across to the base. So the base tracks the emitter 0.7 volts higher, being a NPN transistor that we're working with. The voltage across RB has to decrease if the voltage on the base increases. We've got a fixed potential there of 15.3, so the voltage across RB decreases and the current drive gets lowered to the transistor. Here I've indicated using a hot soldering iron and heating the transistor up. You know, we don't normally write big essays in electronics engineering. We tend to use little icons to indicate what's happening. So if we heat the transistor, force heat it, beta goes up, VE goes up, VB goes up, VBE goes down, and the voltage on the collector increases. Therefore, the transistor has to conduct less. Here's a photograph of the breadboard, and there again showing what I'm about to do with the soldering iron, that is to heat that transistor up. First of all though, we'll have a look at the circuit conditions with the transistor running at room temperature. At room temperature, the voltage between the base and emitter is 561 millivolts. Spot on, exactly where you'd expect it to be, about 0.6 to 0.7. 0.7 is a really hard driven transistor. 0.56 small signal transistors quite often run around this value. But now, extreme heating. Well, it's pretty extreme. The soldering iron on top of the BC547, being careful there not to burn the multimeter or anything on the board. And very rapidly I saw that VBE drop, and I snapped the photograph there at 481 millivolts. So VBE got a lot lower as the transistor heated up, and that's going to lower the BJT currents and stabilize the circuit. And this stabilization all comes about because we've got this emitter resistor. If we didn't have that emitter resistor there, we'd have a very wild circuit that could easily get into thermal runaway. And we don't want that situation with either diodes or with BJTs. Just back to there again. Yeah, so 481 millivolts. This slide 9 is quite a large slide as far as graphic content goes. This is the first bit of graphic content which we'll focus on, and then we'll look at this smaller inset later on. So, constant current in the collector circuit over a wide range of resistances. This is something which I don't know how many people I've had in classes over the years still don't understand constant current right towards the end of their course. And it's a shame, because we've got this resistance, variable resistance in the transistor between the emitter and the collector, and as we change the value of the collector resistor, this resistance changes. It's a dynamic resistance. It changes to compensate and keep the current set to where the base and emitter circuit set it to. You'll recall in that very first PowerPoint in part 1, this was coloured in green, this section through this resistor and this resistor. And I said to make that indelible in your mind, because this is what sets the collector current. This is what sets the emitter current, and the IE is equal to IC, so therefore IC is set by this, not by its own resistances. I've got a milliamp meter here in the collector, 15 volt supply. At 1 ohm, tick, 2.76 milliamps. 56 ohms, tick, the same. 560 ohms, the same. 1k ohm, the same. 5.6k, cross. 5.6k caused the transistor to go into saturation, and it had a much lower current, around about 2 milliamps. Now, saturation is also something which is sadly very misunderstood. Most people think that saturation is just when the transistor is working hard and you've got a low voltage across here. So VCE less than about 300 millivolts. Yes, that is true. In the Painter textbooks, that's exactly what Painter says about saturation. And I think he might go on to say it's at the point where the collector current will no longer show increases with increasing base current. But there's a third way. So we've got what Painter says there about the base current no longer affecting the collector current, that's saturation. Less than 300 millivolts across this junction is saturation, but also we've got forward bias occurring between the base and the collector. Normally in a transistor, the collector base junction runs in reverse bias. So if I've got 5 volts on the base, I have to have much more than 5 volts on the collector, so more than 5.6, 6.6, 7.6, 8.2, something like that. It's running reverse bias across that junction. But if this collector voltage was to fall below the voltage on the base, it goes into forward bias across the base collector junction, and that is also an indicator for saturation. So saturation is a forward biased base collector, a collector emitter junction which is less than 300 millivolts, and a situation where further increases in the base current no longer cause a change in the collector current. The 5.6K then, with the cross across it, resistor dropped VCE below 300 millivolts and into saturation. It did each of those other two things as well, so it satisfied all three conditions for saturation. I measured the values. 4.69 volts was on the base, and only 4.26 volts was on the collector with that 5.6K. So we would have needed like 5.2, 5.3, 5.6 volts or something across, on the collector to be reverse biased. At the moment it's heading well and truly towards a forward bias situation. So this is very important, like I said, with transistor circuits, the constant current ability of the transistor, and there's many circuits where we use the transistor specifically for that constant current effect. It's remarkable to note that most everyday circuits which we encounter use either emitter feedback bias, such as the circuit we've just been looking at, or collector feedback bias, or emitter bias, which is the most stable bias you can have. Yet the textbooks concentrate on voltage divider bias, VDB. While VDB is good to know, it's not seen all that often in real circuitry. This is why I will concentrate on the three bias types above. Alright, so that just about concludes part 2. Been the second PowerPoint for the BetaBox series. Other PowerPoints will still follow. Again, if simple base bias is utilised with no emitter resistor, and that from a stability point is a very bad situation. It's only used normally for switching purposes. If we're using BetaBox to solve it, we don't need any resistor equalization. If voltage divider bias is used, and I've still got to do this in part 3, a Thevenin's equivalent model needs to be made of that voltage divider. Otherwise, the same technique applies to divide the base resistance, even though it's Thevenized base resistance, to divide that by beta, and then do the other steps as we saw with the emitter feedback circuit. All the slide content is original by yours truly, and feel free to share it. Creative Commons share alike with attribution. Alright, that winds up part 2. Thanks for watching, and if you enjoy it, please subscribe to the channel. Bye.